Let's talk about fluid depth. So hydrostatic pressure on a solid is calculated the exact same way that it is calculated for a fluid. And so that leads to a couple of general rules. Let's get to something other than red here. And so that first general rule is going to be that a fluid acts in all directions. Well, fluid pressure acts in all directions and is always perpendicular to the body. To the body. And so the second one is fluid pressure is constant at a constant depth below the surface. Now this one's important. We're going to be exploiting this a lot, especially next week. Actually, below a free surface. Let's be technically correct there. So as we look at things, let's take a look at this picture here. So I have water. I have atmospheric pressure pushing down on this water. And as I look at, I have my depth 1, little a, little b, little c, little d. And the question becomes, which one has the highest pressure? Now, of course, this is a trick question. And I know the column of B is a diverging cone. Column C is, is a converging cone. Column C is a diverging column. Column D is a little bit smaller than A. But it doesn't matter because they're all at the same depth. They will have the exact same pressure. It does not matter what the container looks like. Now, we can look at depth depth 2, and we've got capital A, B, and C. Now, which one of those has the highest pressure? Well, A, B, and C all have the same because they're at the same depth below this free surface here of water, so they'll have the exact same pressure. D is a little bit different because D has mercury on top of it. Think back to the hydrostatic equation is all based on gamma, the specific weight. The specific weight of water is much less than the specific weight of mercury. So actually, to calculate out that mercury, we'd have to run the hydrostatic equation twice. We'd have to run it between point 1 and point 2 to find out what the pressure at point 2 is, and then we'd have to run it between point 2 and D and add those together. So it's basically we have the air pressure pushing down on top of the water, I have the water pushing down on top of the mercury, I have the mercury pushing down at point D. So on this one, D is going to have the highest pressure just because mercury is so much heavier than water, and it's going to add that extra weight. And so the last thing is we can utilize this for mechanical advantage. This is used a lot in hydraulic jacks, brakes, power steering, basically any hydraulics application. So if I look at this, and I've got this and this plates are at the exact same depth. Well, that tells me that that pressure at 1 has to be equal to the pressure at 2 because the hydrostatic equation tells me fluids at the same depth have to have the same pressure. And so how do we calculate out pressure? Well, you can see that force is the pressure times the area. So pressure at 1 is going to be the force of 1 divided by A1. Pressure at 2 is going to be the force of 2 divided by A2. And those all have to be equal. So what we can do is we can say, okay, well that means that force 1 over area 1 has to be equal to force 2 over area 2. And then we can rewrite that in any form that we want. So if we were trying to say that we were amplifying force 1, well, force 1 will be area 1 over area 2, force 2. And so you're able to use that mechanical advantage using fluids instead of using like a pulley system to amplify your force. So of special note while we're here is this concept of what we call the pressure head. We'll talk quite a bit about this later on in the class. And the pressure head is kind of the hydrostatic equation, just written a little bit differently. And that's going to be that H is that distance between point 1 and point 2 is going to be the change in pressure over the specific weight. And so this is the height of the column of fluid that gives you that pressure difference. Case in point, if I wanted to talk about 10 psi, I could talk about the height of the column that represents 10 psi. So if I wanted to talk about 10 psi different as a pressure head, well, notice that it's talking about the specific weight of a fluid. So we can express it as a linear measurement, because that's what Z1 minus Z2 is. So if I take 10 psi, I plug in, that's my pressure difference, I plug in my specific weight of the fluid, I can say that 10 psi would also be 23.1 feet of water. And it's important that it's not just 23.1 feet, because it's specifically tied to water because of the specific weight. If I wanted to use mercury, that would be 518 millimeters of mercury. Now that's about a half a meter, so about 1.5 feet. And this is why you hear when they talk about pressures a lot, especially when we're talking about barometric pressure, they're always talking about inches of mercury instead of inches of water, because since mercury is so much more dense, we can make a much shorter measurement with that.